So if expressions are equivalent, they simplify to the same expression. They simplify to the same expression. That's the easiest way to determine if two expressions or three expressions are equivalent. So notice like here, I'm going to distribute. 3x, 3 times negative 1 is negative 3 plus 4. Negative 3 plus 4 is 1. So right away, I can actually stop. Is 3x plus 1 the same thing as 3x minus 1? No. So those would not be equivalent. But notice if I distribute here, I get 3x plus 1. Does that make sense? Like, using a very simple case, if I simplify those expressions and they're the same, then they're equivalent. We good on that? Donovan, you good? Okay. Okay. So that's what we want to be looking towards. And then there's lots of different ways to determine if they're equivalent. For instance, if I were to look at number 13, if I were to start looking at the rest, what I would note is, oh, well, a negative exponent tells me to what? What is a negative exponent? To divide, right? So instead of writing 64 times 2 to the negative x, it's just 64 divided by 2 to a positive x. And I might do that because, hey, that's exactly what I have here in the second slot. And then I might have to play around with it a little bit, but that'd be 64 times 1 to the x divided by 2 to the x. Well, what's 1 raised to any power?
1.
That's 1, right? So 64 divided by 2 to the x. Does that make sense? But that's only one way to do it. Okay, that's not like, hey, this is the only path you can take. If I'm looking at 64 times 2 to the negative x, I can actually rewrite 64 as 2 to the 6. That's how I created a common base. Because what can I do now that I'm multiplying numbers with the same base?
Add 'em.
So 2 to the 6 plus a negative x, or just minus x. Right? Same thing with the second one. I've got 64, which is 2 raised to the 6 divided by 2 to the x. What do I do when I have words,
Subtract.
slow it down. What do I do when I'm dividing numbers with the same base?
Subtract.
Subtract. 2 to the 6 minus x. Are those equivalent?
Mm-hmm.
And then 64 times 1 divided by 2 to the x. Well, I could go ahead and write 64 as 2 to the 6. Because I'm doing 1 divided by 2, I could rewrite that as 2 to the negative 1, then being raised to the x, right? So there's more than one way to approach this. What do I do when I raise a power to a power?
Multiply the power.
Again, are they equivalent? And I want you to know this, and I think this is one place where a lot of students get really hung up in math. They're like, I don't know how to do this. Well, there's not just one way to do it. There's lots of ways to approach it. What's easiest for you? Personally, I thought that was much easier. You may not have seen that, though. Maybe you saw that, hey, there's all base 2's there. Then work with it. Right? So look for something you do know. This one here should have been a little bit easier. Because I will say, like with 17, there's not a whole lot you can simplify, but when I look at 20, or not 17, the first part of 17, when I look right here though, what do I do when I raise a power to a power? So I got 20 times 1.1 to the x. Same as what I started with, right? And then what do I do again when I raise a power to a power? Multiply, right? So when I have 20 times 1.1 to the 1/5, raise it to the 5x, so times 5x was 5 divided by 5. So again, notice how all three of those on number 17 simplified to the same expression. That's what we're looking for. Bless you. Alright, any questions about 27 through 29 before we continue with today? Alright. You can keep 2.6 out because you may want it for some help and some ideas today. So I don't have to start writing a ton of people's names on 2.7 because we are missing a ton of people. I'll do that in a second. So 2.7 is what we are starting today. It's what we'll mostly be focusing today's attention on. One thing I do want you to notice right away at the very top, you should see an a raised to the m divided by n, and then the nth root of a to the m. Does it look like something's missing there? And I will tell you the reason I'm asking that. Yes, there is something missing.
Equal sign.
An equal sign. Those two things are supposed to be set equal to each other. You can also put the equivalency symbol, but the equal sign is appropriate as well. So I'll show you that again in a second. So we're about to look at our objectives, and in 2.7, radical ideas is what we're working on all day today. So here's our objectives. Can y'all read that red from back there?
Kinda.
So I need to choose a different color moving forward?
Yeah.
Cool. It's so weird because like you can look on my laptop and it's so clear, and then we put it up here on the projector and it's
I
like,
like if the lights are on out here too.
let's see how it looks with the lights off.
That was better.
Is that better?
Yes.
Okay. Donovan, can you read our first objective for us today?
I can convert rational exponents to the roots of numbers and roots back to the rational exponents.
Okay. McKay, can you read the second one?
I can use the properties of exponents to simplify that.
Okay. And Linnea, can you read our last objective?
I can determine if I prefer rational exponents or radicals, but I can use both representations.
Okay. So have we done some practice of converting back and forth between rational exponents and roots, the radicals?
Yeah.
We've done that a little bit, right? We introduced it a little bit more heavily in the last lesson. But going back and forth between roots and rational exponents, have we used properties of exponents before?
Yeah.
Yes. Now, maybe not a ton with simplifying radicals, but I will, maybe not here as much. We'll look at it in a second. But, I mean, we've used properties of exponents. We've simplified radicals, so we're going to put those two together. But separately, neither of those are brand new. And then here, you do need to be able to determine if you prefer rational exponents or radicals. Because remember, a rational exponent is a radical, just written in a different form. I don't care which one you use. You need to figure out which one you're comfortable with. Does that make sense? You good with that idea? Yes, Mr. Kenny, we're good. Thanks, guys. First things first. I want you to notice, alright, notice there's not the task on here yet, it's just this bit of information. We're going to recap a little bit here. But you see under 2.7 radical ideas where it says a practice understanding? This idea of a practice understanding means that we have been working with radicals, we've been working with rational exponents, and so now we need to practice going back and forth between them. This is going all the way back to 2.4. So 2.4, 2.5, 2.6, this is the practice task to go along with those lessons. And so whenever we come upon a practice task, that's when you should start to expect an understanding check to come up. There's always a develop understanding task first, a solidify understanding task to help you understand those ideas better, and then a practice understanding. Whenever you see practice, be like, hey, understanding check's coming up. Okay, so here's the thing. The first time you ever started dealing with exponents, they were exponents like this, 2 to the 3rd or 3 to the 7th, right? What kind of exponents were those always?
Natural.
Natural numbers, weren't they? So the natural numbers, and we've already defined this on our graphic organizer, but so just give me a handful of natural numbers.
1,
Okay?
2, 3, 4.
147.
Say again.
Said 147.
Okay. So 1, 2, 3, 4, 947, whatever you want it to be, right? These are the positive integers. And I want you to make this note to yourself. When you have exponents, right? And a natural number is the exponent. what is that natural number going to tell you to do? Repeatedly what?
Multiply.
By?
Itself.
Okay, starting at what number though, technically?
1,
Okay, times 2, how many times?
3 times.
Right, so we want to make a note with exponents multiply 1 by the base n times, right? That's whatever the exponent is, so let's say a to the n. Right, so when we have an exponent, that's when you first learned about exponents. But then we get to whole numbers. What number do we introduce when we get to whole numbers?
0.
We introduce 0. Is there anything else in whole numbers?
No.
No. Okay? It's the only extra number in whole numbers. So what I'm going to do is I'm going to say it's 0 plus the natural numbers. So if I get a to the 0, what did we learn? Doesn't matter what the base is. What's anything raised to the 0 power?
0. 1.
Which one?
That's 1.
Mona, you think it's 0 or 1?
If you multiplying, right? If you multiplying, it's always gonna be 0 if it's times, like.
Okay. So Linnea, do you think it's 0 or 1?
1.
You think it's 1? Donovan?
0.
Think it's 0? 0? Okay, so Mona said anything multiplied by 0 is 0, but Linnea and McKay, you're saying you think it's 1. Linnea, why do you think it's 1? You just feel like you remember that?
Yeah.
Okay, how about pick up a calculator? I don't care what base you put in. Let's do 3. What's 3 raised to the 0?
1.
1. What's 5 raised to the 0? 17 to the 0. 1. So what do you think a raised to the 0 is?
1.
Okay? So here's what I need you to remember, and Mona, this is an important detail. Am I multiplying by 0 right now? It's not a times 0. We need to recognize this. Remember how 2 to the third was 1 times 2 times 2 times 2, right? Starting at that 1 and then multiplying by how many 2's?
3.
3 of them, right? So if I were to have 3 to the 0, what number am I still going to start with?
1.
1, but how many 3's am I going to multiply by? 0. So remember, Mona, it's not multiplying by 0, it is multiplying by 0, 3. So I just don't have any 3's. Right? Whereas if I were to do 3 to the second, I'm starting at 1 and then multiplying by 2 3's. Does that make sense? So a to the 0, right, when we introduce the whole numbers, that 0 there, anything to the 0 power is 1. That's a new exponent rule. Then we moved into
Integer.
the integers. What numbers do we add in with the integers?
Negatives.
Negatives, right? So we have the whole numbers plus the negative whole numbers. That sounds kind of awkward, but notice if I take the opposite of every whole number out there, I get the integer, right? Or the integer number set. So 2, negative 2, 3, negative 3. So if I take my whole numbers and I add to it the opposite of the wholes, I get my integers. So what happened when we started to use the, which we've already done wholes, if I started to look at the negative wholes, if I had 2 to the negative 3, what was that? 1/8, because what is a negative exponent?
Division.
Repeated division, right? Remember, I'm still starting at 1, but how many 2's am I dividing by?
8. 4. I'm not 3.
It's 2 to the negative 3, so it is 3 2's, right?
Mhm.
So if I were to have a raised to the negative n,
1.
Not just 1, 1,
A, N.
right? So we want to recognize this pattern. The natural numbers, hey, with those exponents, we were multiplying 1 by the base n times. Then when we introduce the 0 for the whole numbers, well, then I'm not multiplying by that base. I introduce the negatives for integers. Instead of multiplying, I'm now dividing because that's the inverse. And now we have introduced the rational numbers. Like 1/4. In general, what do we mean by rational numbers? Should slow down and make sure we detail that. So it does include all well, not all decimals. So yes, it includes decimals. But what kind of decimals?
Fraction.
So anything that can be represented as a fraction of whole numbers, right? So see how it's a ratio? So it is a ratio of one whole number to another whole number. I'm going to say A sub W and B sub W. I'm just saying that for A is a whole number, B is a whole number. Okay, so a rational number is a ratio of two whole numbers. And so repeated multiplication, not multiplying by anything, repeated division now, what is that rational exponent going to do? What is the point of having a rational exponent? No one remembers what a to the 1/4 would be?
Fourth root.
Thank you.
A1.
That'd be the fourth root of a to the first, right? We want to recognize and keep in mind that these rational numbers are important because they're what undo powers. The fourth root undoes a fourth power. A cube root is going to undo a third power, things like that. And so, that brings us to this point. Well, first off, do we have these notes or we understand these ideas if we need them? Where else can you find these number sets?
Graphically.
That graphic organizer. On that graphic organizer, I did not include these details about those, how they would appear within exponents, but that is important to notice, right? That natural numbers give us the repeated multiplication. Adding that 0 in tells us, oh, we're not actually multiplying by the base at all. The negative exponent, okay, I'm actually dividing by that base now. And then when we get to those rational numbers, we're talking about roots of numbers. Any questions before I erase this? Going once. Going twice. Sold. All right. So, please note, and this is what I was talking about earlier, that equal sign is missing on your paper. Make sure that a raised to the m divided by n equals the nth root of a, all raised to the n. So if you have not already put that, make sure you get that. So, now that Tia and Tehani know that this is true, they are wondering which form, radical form or exponential form, is best to use when working with numerical and algebraic expressions. Tia says she prefers radicals, since she understands the following properties for radicals, and there are not too many properties to remember. If n is a positive integer greater than 1 and both a and b are positive real numbers, then the nth root of a to the n is just a. So if the root and the power are the same, what do they do to each other?
Cancels out.
They cancel out, right? A big part of simplifying radicals is just simply understanding, hey, if the root and the power are the same, they cancel each other out. And we can use that in a lot of these situations. The nth root of a times b is just the nth root of a times the nth root of b. The reason why you might want to know something like that is, let's say I have a cube root of x to the 5th. Well, Looking at the cube root of x to the fifth, is the root and the power the same? Can I rewrite x to the fifth though, so that maybe there is a power that is the same as that root? Anyone know what that would be? So if I have x to the second and x to the third, now one of those roots is the same as the power. So now I can use that idea that I can split them up. What is the cubed root of x cubed?
Hold on, how you get x?
John, even here,
Yeah.
I created an example so that we could illustrate why this is important.
Oh.
I just made an example so that we could apply this and understand why it's important.
So the same way you would do that, you do it for that problem.
Say that one more time.
The same way you did that example, that's the same way you do it for that problem.
Well, this could be two different numbers. What I'm saying is, hey, if we're multiplying two numbers like this, I can split it up into the nth root of the first number and the nth root of the second number, which is useful when simplifying right here, because that 5 is not the same as the root, right? But x to the fifth is the same as x squared times x cubed. That is the same as x to the fifth. Now I split it up, and now notice what is the cubed root of x cubed. Remember, if the root and the power are the same, they cancel. And so then I would have to leave it as the cube root of x squared. So it's just how can we use that? In the same way, when it's the nth root and they're being divided, you can split it up into the two divisions. It's two different things being divided. Notice how many rules are there when you're dealing with a root?
0.
What? How many rules are right there?
3.
3, right? So Tia says she prefers this method. There's only 3 rules and she likes that. But Tehani says she prefers exponents because she understands the following properties for exponents. Now notice Tia kind of had to use some of these. So we're multiplying two numbers with the same base. What can we do?
Add 'em.
Is McKay the only one in class today? Donovan, you awake back there? We're over there? Donovan. Alrighty then. So we add those exponents. Linnea, what do we do when we raise a power to a power?
I want to say subtract.
Is that what you see right here or on your paper for number 2? I'm going to turn these lights on. We are too close to falling asleep. Say again?
Multiply.
Multiply them, right? When we raise a power to a power, we multiply them. And please don't forget, don't feel scared to do this. If you need any of these explained while we're working through this task, please ask. I'll be more than happy to explain them. Okay? So I can explain where they come from. So when we raise a power to a power, we multiply the powers. Now this is a little bit different. We haven't done this before, but notice if it's a times b raised to the n, that's a to the n times b to the n. Isn't that exactly what we're doing here with the nth root? Right? The nth root of ab is just the nth root of a times the nth root of b. Same detail. Right? And if we're dividing them, a divided by b raised to the n is a to the n divided by b to the n. Same thing as number 3 for roots. Because roots and radicals, or roots and exponents, those rational exponents are the same. And then if I'm dividing two numbers with the same base, subtract those exponents. And then if it's a negative exponent, I'm dividing. We're taking the reciprocal. All those rules are there. We've studied them before. So here's your job. First off, illustrate with examples.
Oh my God.
You just scared the crap out of me.
Same. Hey Mona, I can rewrite it. It's okay.
Oh gosh.
Alright, I'll rewrite in a second. So right now, Illustrate with examples and explain, using the properties of radicals and exponents, why a raised to the 1 divided by n is equal to the nth root of a, and a raised to the m divided by n is equal to the nth root of a to the n. Right? Why are those true identities? So take a few minutes, talk about that with your group. Mona, I'll rewrite that stuff on the board, okay? But talk about this with your group and try to think through, okay, so why are these things identities? When we say they're identities, they're things that always are true. So go ahead and talk through this and we'll come back together in a few minutes.